Hey everybody, my name is Mark Latham. I'm a space systems engineer and an astrophotographer, and I wanted to talk to you about the recent discovery of a black hole. This thing is only 1,000 light years away, and it actually is 4.2 solar masses, larger than anything in our own solar system. The thing that blew my mind is this being so close as it is, 1,000 light years away, black holes are massive. I was wondering if there's any possible way we could measure its gravitational effect on all of us just living on the surface of the Earth. As a space systems engineer, I've worked on multiple projects, one being the NASA Gateway Space Station that's going in orbit around the moon. And so I feel like I can do some math, but I'm steering clear of anything with general relativity. I don't want to be doing any calculus because all you need is Newton's theory of gravity, or equation for gravity, which is the gravitational constant, the two masses multiplied by that, and divided by the distance twice. So I've got all these numbers lined out, hopefully giving us context for what is a gravitational pull that we can be used to in our everyday lives. If you run the numbers for this 4.2 solar mass black hole at 1,010 light years away, you get 378 attonewtons. And I have never heard of an attonewton before. I have no appreciation or context for what that force actually translates to. So sticking in the gravitational realm, I continued outward and tried to figure out other cosmic sources for gravity. The obvious gravity that impacts every single day of our life is the Earth. Coming from the Earth, we actually have 609 newtons every single day, averaged out to the typical body weight of 62 kilograms. That is enough to dictate every single act in your life. If you're pouring water, sleeping in your bed, putting on a shirt, everything is impacted by the 609 newtons from the Earth. If you look at the largest thing in the solar system, well beyond 99% of all the mass in our solar system is the sun. But at its distance, the pull from the sun on each and every one of us is only 0.37 newtons. That's hardly a third of a newton, when a full newton is supposedly the weight of an apple in your hand or close to that. It's interesting to think that when the sun is in the middle of the sky, you're about a third of an apple lighter. Of course, your body weight fluctuates more than that throughout the day, but that would be a wonderful video that I'd like to see if I could actually measure that personally, the difference from the sun pulling on you during noon or from sunrise to sunset. The next object I calculated gravity for was the moon. This blew me away. It only comes out to 2 millinewtons, which is significantly less than the sun. Mars, for this calculation, has a distance of 34.8 million miles. That's the closest it usually gets. Now, with the force of 850 nanonewtons, we're well in the small number range. Nano in front of the newton means that we're dealing with 1 billionth of a newton. And 1 billionth means we have 10 to the negative 9 zeros after the decimal place. It is absolutely difficult to think of anything that compares to that. But what is an example of something that's closer to us in that range of nanonewtons? One person talking to another person in a conversation 1 meter apart, that comes out to 260 nanonewtons. It's amazing to think that you actually have a gravitational effect on all the things around you. And when it comes to things that are beyond comprehensively huge, let's say the Virgo supercluster, this thing is 65 million light years away with a mass of 1.5 quadrillion suns. And the Virgo cluster in the night sky, wherever it is pulling on you with 38 piconewtons of gravity. That's piconewtons. That's a whole nother 1,000 down below nanonewtons. We actually have it representing a trillionth of a newton, or with the amount of zeros of 10 to the negative 12. And it just keeps on getting more hard to comprehend how small these numbers are, with something being as small as a smartphone per se. If you put that on the other side of the room, it's charging on a table 7 meters away, that comes out to 14 piconewtons, which is actually the same amount of gravitation coming from the Andromeda Galaxy in the night sky. It's crazy to think that the Andromeda Galaxy has less gravitational pull on us, despite us being so much closer to it than the Virgo supercluster. So my next thought was, what is the largest building that humans have ever made, and how much mass did they have to move, and how does that mass impact me? The Great Pyramid of Khufu, sitting in Egypt, is pulling on me in Los Angeles through the core of the Earth with 170 femtonewtons. This is a quadrillionth of a newton, or 10 to the negative 15. And this range of femtonewtons is actually the same amount of gravitation coming from the Orion Nebula in the night sky. The Orion Nebula is 1,300 light years away, which actually is the same ballpark as this black hole, distance-wise. So here we are, back at 378 attonewtons. And you gotta just question, where are we? Attonewtons represent 1/quintillionth of a newton, or 10 to the negative 18. Why should we even care if we're already down to a quintillionth of a newton? Is that actually measurable in any way? UC Berkeley in 2014 made a world record. They measured a force all the way down to 42 yoctonewtons. That's a number I had never heard of, yoctonewton. Now they sort of cheated. They actually used a lab. They had mirrors and lasers bouncing through extremely chilled atomic clouds to make this measurement. But this is at the heart of many of the most incredible discoveries in science. I love comparing this to the LIGO detector, the detector that actually discovered gravitational waves from black hole collisions. They needed to be able to measure the change in distance equal to 1/10,000th of the width of a proton. The equivalent of that measurement is the distance from Earth to the closest star, having that accuracy down to the width of a human hair. I'm completely amazed that so much money, technical talent, and just sheer force of will goes into measuring something so incredibly small. And to think that a yoctonewton, 10 to the negative 25, has been measured before, when the force from this black hole, 1,000 light years away, is 10 to the negative 18? That is thousands and thousands of times stronger. So these are extremely small numbers, but let's go ahead and compound them up over time. If you take the smallest force, 42 yoctonewtons, and every day, just once a day, you increase it by 1,000th of its value. You do that for 150 years, you'd actually end up with 1/2 of a newton, which is also comparable to the force from the sun, or is the same amount of force behind a screen tap on a touch phone. And please go ahead and expend this 1/2 newton on the like or subscribe button. I put a lot of work into this and I'd love to bring more content to you in the future. One final thought here. With Newton's third law, it states that for every action there's an equal and opposite reaction. If all of these forces are impacting your body is also sending those same forces back. And those cosmic structures, the sun, the earth, Mars itself, the Virgo supercluster, are having equal and opposite reactions from your presence in the universe. Imagine just snapping your fingers Thanos style and having your atoms just disappear from existence. Sure, the universe would keep spinning away, but it would spin away in a completely new and different manner than if you had existed in it. Which brings all this down to the root takeaway that I have, is that all these numbers may be incredibly small, but it doesn't mean that your matter doesn't matter. Thank you so much for watching. I cannot wait to get more of this content out to you. And hopefully next time you look up at the stars, they'll feel a little closer because they want to be.